Hello, and welcome to another episode of Phys 3500 Classical Mechanics with your instructor, Dr. TJ Hammond. For this lecture for Monday, October 5th, we'll be still covering Lagrangian and Hamiltonian dynamics, chapter 7 from your textbook. So further notes, assignment 3 is now posted. I normally post the assignments Thursday night, but I had forgotten to upload it, so it is now available for you. It is due Friday. We'll be covering problems 7.4 and 7.9, the ones we didn't get to last Friday, on Friday. So you'll be able to see more examples. They're actually more relevant to what we'll be covering this week anyways. The daily assignment will be to convince yourself that equation 7.138 is correct. And we'll see what equation 7.138 is towards the end of lecture. And this will be due Wednesday. So what are we covering this week? We'll be covering sections 7.6 to 7.13 in your textbook. That will be covering the equivalence of Lagrange's and Newton's equations. So we've already shown that there are some instances of this, such as like simple harmonic motion, or we had it for like a free particle. But we're going to do this another way just to convince you that the formulation that we have for Lagrange's equations are formally equivalent to Newton's equations. Okay, so we get the same equations of motion, therefore the physics must be the same. We'll also be covering in this lecture equivalence of symmetries and conservation theorems. So this is Noether's theorem. So Emmy Noether was a famous mathematician and physicist from the early 1900s. And she came up with recognizing that symmetries led to conservation of various properties, which have fundamental repercussions in physics, from quantum mechanics to general relativity. So we'll use the symmetries in physics to simplify problems, and this will be kind of like a formalism on how to expand on this idea. We'll also be covering Hamiltonian dynamics. So far we've only been using Lagrangian dynamics with Hamilton's principle. Now we'll be actually seeing what Hamiltonian dynamics mean. So the Lagrangian is T minus U, the difference of the kinetic energy and the potential energy, but the Hamiltonian is the sum of the kinetic energy and the potential energy. This is kind of a specific case of it, although often this will be the result. It's slightly different formally written, but basically it means that the Hamiltonian is going to be the sum of the energies, which you know from before is conserved, especially for a conservative system. I'll be going through the equivalence of Lagrange Newtonian mechanics. I've been getting some comments saying that people like it more when I actually go through the derivations in class rather than just kind of have them there and read through them. So I'll actually be going through the derivation for you guys. Now, when we show that Newton's laws and Lagrange's equations give the exact same equations of motion, then that means that there's absolutely no physical difference between the two descriptions. So that means we get, the x double dot has to be the same for Newton's that we derive from Newton as the same as we derive from Lagrange. So that means that we get the exact same equation of motion, which means that we'd integrate that to get the exact same trajectory. But the thing is that philosophically, these mean something differently. And so this is maybe something that you're already kind of familiar with when people talk about, say, quantum mechanics, and they talk about, say, like wave-particle duality, or they talk about how to interpret the results of quantum mechanics or something like that. You'll have this wave function collapse, or these things like that. Physically, we all use the exact same equations, but it's how we interpret what these equations mean. So when we set up from Newton's laws, we have a force that acts on a body. This body has a mass, therefore it has some momentum. And this is the idea of cause and effect. So we have some force that acts on something, and that something then moves. So it's a cause is this force, and the effect is the motion of this particle. Now Lagrange's equation, through Hamilton's principle, means that we're going to find the path of least time between the kinetic and potential energies, right? So L equals T minus U. And what we want to do is minimize this action, right? And so philosophically, what we're saying is that nature wants us to have the least action possible, and that is what leads to the equations of motion. Now, this might seem a little abstract to you, and this is initially kind of more of an abstract concept, but you can think of it in terms of the geodesic of a sphere that we looked at earlier, right? So we saw that the shortest distance between 2 points in regular free Cartesian space is obviously going to be a straight line. And then you showed on your assignment that the shortest path on the surface of a cylinder is going to be a helix. And then we showed that this shortest path on a sphere is this geodesic of a sphere, which was a plane intersecting the sphere through the center of the sphere. And so basically that's going to be the same thing that we see in nature when we have, say, like a gravitational force or something like that. And this becomes extremely important in general relativity, that if you're, instead of having this orbit, basically from Newton's equations, you have this force of gravity that's attracting this planet or this object, and it's causing this orbit. It turns out that for general relativity, you look at time and space as coupled, and then you say, okay, this is going to be a geodesic in this four-dimensional space. So it becomes really, really important as we get to higher concepts in physics. So we won't do general relativity in this course. It's of course a graduate level course, but it is something that it's like a fundamental difference way of looking at it. And so people will talk about the geodesics in four-dimensional space is a really common thing in general relativity. So so now maybe you're starting to see, this is a typo, some benefits of using the Lagrangian. And so using the Lagrangian dynamics, I've talked about this last week. So kinetic and potential energies are scalars, and so that's nice because it's just a number as opposed to forces, which are vectors. But because they're not vectors, because they're just scalars, we can actually these scalars are invariant to coordinate transformation. So this was actually mentioned in the very first lecture. If we have a mass of, say, 4 kilograms in Windsor, and we move those 4 kilograms to New York, it's still 4 kilograms. So it doesn't matter if we transform these coordinates from Windsor to New York, it's always going to be the same thing. It's 4 kilograms. But if we had something that was related to a vector, then we'd have to change that vector as we change this coordinate. And so that means that because these are invariant to coordinate transformations, these coordinates can become generalized, and they help us simplify the problem. And we'll be dealing with some of those examples later in the week. All right, so one of the main points that we'll be discussing, in this lecture and this week is ideas of conservation. So as I said at the beginning, this course is only concerned with conservative forces. And so that means that we don't have any kind of dissipative forces, so we don't have things like friction or drag or whatever. And so what that means is we can use these kind of idealized cases. So if we have conservation of energy, then that means that this characteristic, it means that the energy doesn't change as a function of time, okay? So energy is conserved means the energy from time 0 is equal to energy of time, 100 seconds or infinite seconds. And so we have this, this characteristic is maintained, the energy is conserved, and so we have this characteristic of time, and this property of the Lagrangian is invariant to time. And so that means that the conserved quantity is total energy, the kinetic energy plus the potential energy. Now when you have conservation of linear momentum, the characteristic is space, and what we mean about linear momentum is that if we change the Lagrangian by some amount, say delta x, then this doesn't actually change the Lagrangian because we haven't we haven't changed anything in space, and so this is invariant to translation, and that allows us to have linear momentum conserved. We also have the conservation of angular momentum, and that is when space is isotropic. And so what that means is that if you're looking in any direction, so if you look to your front, to your back, to your left, to your right, up or down, or at 45 degrees in any direction, it looks the same. That's called isotropic. And so what that means is that the property of the Lagrangian is invariant to rotation. So that means that whatever you had and you rotate it by, say, 10 degrees, or you rotate it by 80 degrees, everything still looks the same, then it's invariant in that rotation. That means that angular momentum will always be conserved. And remember when we saw central forces, that we had angular momentum was conserved, and that's going to be the same thing here. So if we had a central force, this force is only acting radially, so that means that the potential energy is only a function of r as well. And so that means that if we rotate this by any angle theta, we don't see a difference to this potential. We don't see a difference to this system. All right, so we'll go through the derivation of these in class, but the daily assignment will be understanding this equation here, that delta r, this vector, is equal to delta theta cross r. So our original r vector is here. It's pointing from some point on the origin up to some position here, and then we're going to rotate slightly by delta r, and that means we're rotating by delta theta, and so we go from r to r plus delta r. And what I want you to understand is that this delta r is going to be delta theta cross r. Okay? So we'll be showing this in class, but I know that students will have a problem with this because this is a three-dimensional object. This thing is rotating into the board. And so this becomes a little bit difficult to visualize, so I want you to try and convince yourself of doing this. We'll also show this in class, but if you kind of sit and think about it, then maybe that'll help you to understand it. All right, so that will be it, everything that we cover in lecture. This might lead a little bit to Wednesday's lecture as well. Yeah, so we'll be kind of continuing on with Chapter 7.